Okay, so welcome back. This is going to be the third video in the series. This is probably still the first, still in the first live class. And so what we ended last time saying that we have this situation where we have two kinds of things in the world that we're interested in. Right? We have particles that are discrete, they're countable, right, and they have well-defined trajectories. They're at a particular position at a particular time, right? They're moving at a particular speed. You can trace out a well-defined trajectory for each. We also have waves that are more continuous. They're delocalized, right? It's hard to say how many there are, and they're described by a wave function that is a pattern in space that changes in position and time. And these two different kinds of behavior need to be combined. Right? Quantum physics tells us that we need to combine these two very distinct types of behavior and have everything in the universe behave a little bit like a particle and also a little bit like a wave. So in this lecture, we're going to talk a bit about what that means and try and give you sort of a qualitative sense for that. And then in the next lecture, we'll do a little bit of math about exactly how these things work out, because at some point it's a physics class, you need to do math. So we'll split those two things up, and hopefully that'll work. So when I say that I want to combine, I want to have particles that behave like waves, right, and waves that behave like particles. Right, I have two particular behaviors in mind when I talk about that. And there are these two essential equations that show up in quantum physics. The first of these, introduced by the smiling French gentleman on the left here, has to do with the wave nature of matter, that things like electrons that we think of as particles, right, have some wave character to them. All right, and this is introduced by this fellow whose name is Louis de Broglie. And he suggested that a particle with some momentum should have a wavelength that's inversely proportional to their momentum. So that is, the wavelength lambda is equal to some number divided by the momentum, right? H over p, or h over m times v. All right. So this says that a thing that's a particle has a wavelength associated with it. The other half of this description of nature comes from the bald-headed gentleman on the right, who's the German physicist Max Planck, and he introduced the particle nature of light. And he says that a beam of light that everybody thinks of as a wave can in fact be described as a stream of particles, with each of those particles carrying a discrete amount of energy that's equal to some number times the frequency. Or since this is light, it moves at a constant speed, some number times the speed of light divided by the wavelength. So we can move back and forth between the photon energy from the wavelength or from the frequency. In both of these equations, you see this number h. This is referred to as Planck's constant, because he's the first one to suggest it. And it is a very, very tiny number. Right? Planck's constant is 6.626 times 10 to the minus 34 kilogram meter squared per second. Right? This is the number that converts from frequency to energy if you're talking about light, or that converts from momentum to wavelength if you're talking about particles. Right? And it's called Planck's constant in honor of Planck. And this is the fundamental number. If you see this h showing up in an equation, you're dealing with something quantum. Now, just as a brief matter of notation, as we talked about last time, right, we can also rewrite our waves in terms of angular quantities, an angular frequency omega, that's the regular frequency multiplied by 2 pi. And we can talk about a wave number rather than a wavelength. This k, that's 2 pi divided by the wavelength lambda. And we can state these same basic relationships using that notation. So the momentum is h bar times k, or the energy of the photon is h bar times omega. Here, this h bar is a lowercase h with a line through the vertical. This is the reduced Planck's constant. It's Planck's constant divided by 2 pi. We give it its own symbol because we get sick of writing h over 2 pi all over the place. So h bar is 1.055 times 10 to the minus 34 kilogram meters squared per second. Again, very, very small number, crucial for understanding quantum properties of things. So if I want to talk about particles that are behaving like waves and vice versa, I need to have some sort of experiment that I can do that will showcase the difference between these two things. And so what I want to do, the kinds of experiments where you see the difference is when you add waves or particles from two different sources together. They behave very, very different. So I want to imagine an experiment where I'm going to do the same kind of thing with particles and the same kind of thing with waves, where I would see something happen very different for those two cases. So, so what's the experiment? Well, let's think about for for talking about particles, something that very definitely behaves like a particle, like a football, right? Hopefully, it's almost football season. Hopefully, there'll be some football played at some point. The experiment you want to imagine doing is we're going to send a football long distance, say having a field goal kicker, kick it in a fairly random direction, and then we're going to look at where the footballs end up. So, but rather than putting goalposts back there and trying to actually score like we were playing a real game, we're just going to put a detector screen in the back that records where the football hits it. And instead of goalposts, we're going to set this up so that we effectively have two sources of footballs coming in. We're going to put a wall with two slits cut in it that are big enough to pass a football through. Okay, kind of a silly thing to do, but bear with me; it'll become useful. All right. When we do this, right, what do we expect to see on the far side? Well, the kicker lines up, he kicks the football, it flies through the air and ends up at the screen, and we see a football as a particle detected at one particular position at one particular instant in time. Right. That doesn't tell you a whole lot about the pattern. If you really want to see what's going on, you need to repeat this over and over and over many, many times. So you do this a couple more footballs, right? You see some in some different places. You repeat this many, many times. What you'll see is two stripes, right? You'll see two broad stripes where you see lots of footballs, and outside of that, nothing. What are these two stripes? Well, one of them is footballs that went through the slit on the left and hit the screen, and the other is footballs that went through the slit on the right and hit the screen. Right? That's all there is to it. And this reflects the essential nature of particles. They're always at a well-defined position at any instant in time. Right? There's a well-defined trajectory. They definitely go through the right, or they definitely go through the left. Now, what happens if you do the same kind of thing with waves? Well, if you do the same kind of thing with waves, my favorite visual illustration of this is this photo I found on the internet. This is a bumblebee that's fallen into a puddle, and it's flapping its wings trying to get out. Right? And each wing, as a result, is producing waves in the water. You can see the concentric circles of the waves traveling out. Okay. But in this region directly behind the bee, you see something very complicated happening. Right? And what's happening there is the waves from the left wing and the waves from the right wing are coming together. And what happens when they come together depends on the phase between those two. Right? So what you see in this pattern is you see some regions of space where there seem to be really big waves. What's happening there is the waves from the left wing and the waves from the right wing are coming together in such a way that the peaks of one fall on top of the peaks of the other. And that gets you a much bigger peak, a much deeper valley, more prominent waves. This is called constructive interference because you're bringing together two waves and they're constructing a bigger one. Okay. The other thing you see is you see some areas where the water is basically flat. What's happening there is the peaks of one wave are filling in the valleys of the other wave. Right? And when that happens, they cancel each other out. You get basically no wave in those areas. You get flat water. All right, so we have these two different things that happen depending on how these waves arrive, whether the peaks are on top of the peaks or the peaks are filling in the valleys. Right? When they're filling in the valleys, that's called destructive interference because, well, the two waves are coming together and they're destroying one another. You end up with no waves at all. So these are the two kinds of behavior you get from this sort of experiment where you have this two sources of either particles or waves. Either you see two stripes if they're behaving perfectly like particles, or you see a pattern of many different, lots of waves, very few waves, these interference patterns. These are referred to as interference fringes. Okay. So what happens if we do this with things that are behaving like particles and waves at the same time? Well, we can do this same basic experiment with electrons instead of footballs. Right? Electrons, again, they're material objects. We think of them as particles. And this group at Hitachi has made a source that will shoot out a single electron at a time. And they pass it through something that's essentially a barrier with two slits coming in. Right? The electrons could go through the left-hand slit or the right-hand slit. And then they fall on a screen on the far side that's phosphorescent, When the electron hits the screen, it makes a little flash of light. They made this movie of this, and what you see in the movie is each individual electron is detected like a particle. It arrives at the screen at a particular instant in time, at a particular position, and makes a little dot of light. And if we do this over and over and over again, what we see initially looks like a lot of electrons randomly ending up at different positions on the screen. But over time, as we repeat this often enough, we see that the repeated detections of these electrons are tracing out a pattern of bright and dark stripes. Right? These electrons are producing areas where there's lots of electrons detected and areas where there's very few electrons detected. This is not the two-stripe pattern that you expect for things that are perfectly behaving like particles. This is something different. This is an interference pattern like what you see with waves. Right? It's a pattern of multiple stripes that are bright and dark. So this experiment is showing that the electron behaves like both a particle and a wave at the same time. Each electron is individually detected at a particular position at a particular instant, like a particle, but it also, all of them collectively, trace out a pattern that's characteristic of wave behavior. Right? This tells us the electrons are behaving like particles and waves at the same time, and that's the essence of quantum physics. Right? Richard Feynman famously said that this is the only mystery in physics, and if you understand this, understand what's going on here, you can get all the rest of quantum physics from this idea. So these are particles that are behaving like waves at the same time. Now, this being a physics class, we also should do a bit of math about this and describe this a little more quantitatively, what's going on. So that's a very qualitative description of what's happening in these cases. In the next video, I'll go through a little bit of mathematical description of what's going on, what kinds of things we see, and how this depends on various things, and set up the homework that you're actually going to have to do at some point in this class. So, but that's the next video, so stay tuned for that.